Alrighty. So we're here at the last section that we're going to cover for Chapter 9. Pythagorean Theorem and space figures. When we're talking about space figures, we're talking about 3D figures, three-dimensional. Okay, think of a box or even a book. A book is 3D because it has a width, a length, and a depth. Okay, there's 3 dimensions to it. So that's what we mean by space figures. Just like you see here, you have what's called a rectangular solid or a prism. And a prism is not just a box, okay? To be exact, a prism has the same size and shape for both the base and the top. Now, what am I talking about, base and top? Well, this down here would be the base. Why is it the base? Because that is what it is resting on. And it is identical to the top part of this particular prism. Okay, when you have both the base and the top being equal, that signifies that it is a prism. Now, let me show you a little bit of what I mean. Okay, these are prisms. Why are they prisms? I'm going to explain that right now. Okay. For this first one, triangular prism. It's a prism because you have a, oh boy, how many times do I have to say yes? Okay. It's a triangular prism because it has a triangle on the top and on the base. This is a rectangular prism because there's a rectangle on the top and on the base. This is a cube. A cube, which we're going to get to now in a second, is a prism where all 3 of the length, the width, and the height are all the same. So since they're all the same, there's a square, okay, both on the base and on the top. Okay, they're squares. That's why it's a cube. All the sides are equal. This is a pentagonal prism because there's a pentagon on the top and an exact equal pentagon on the bottom. This is a hexagonal prism because there's a hexagon on the top and the exact same congruent hexagon on the base. So when the base and the top are the same, that is a prism. Yes, sir. Yes, these are all prisms. Okay, now, these are all prisms, yes. Does everyone understand why they're prisms? Okay, good. Let's go ahead and get back to work then. So, we know what a prism is. Now, we're going to be dealing with rectangular solids. We're going to be talking with rectangular prisms. And we're also going to be talking with rectangular square pyramids in a second. But let me show you everything that constitutes this particular prism. Okay? We have faces. There are several faces. We have the front, which, okay, sorry about that. The front, which is right here in front of you. ABFE. Okay? You have the back, which is behind it, which is DCGH. DCGH. That's the back. You have the base. The base is this guy right down here. ABCD. ABCD. The base. Okay, you guys with me so far? We also have top. The top is right here. EFGH. EFGH. And then we have 2 sides. Doesn't matter which side you choose. I chose side 1 to be this guy over here, which is ADHE right here. And then you have your second side, which in this case I chose to be BCGF right here. So those are the faces. Yes, sir. Well, correct, sir. The sides of these rectangles, sometimes they're squares, sometimes they are rectangles. What defines the prism is, remember, what it's lying on. Okay? So if it were lying on the sides, for example, if it was lying on BCGF and BCGF happened to be a square, then that would be a square prism. Okay, but since I have a lying on rectangles, it's a rectangular prism. No, it depends. It depends. Yes, sir. Are they ever going to show this figure slanted or tilted? Not in this particular case because we're dealing with a rectangular solid. If we were talking about a slanted figure, that's later on. Okay? Yes, sir. If it had a square base and it went really, really tall, it would be a rectangular prism, depending on where it lied. If it lied on a square here, and you had another square here, okay, and this guy connected to this guy, and this guy to this guy here, and this guy here. In this case, this would be a prism, because you have a square on the top and the bottom. It would be a square prism. If you light it on its side, it'd be a rectangular prism. Okay? Again, there's no need to stress about a prism, guys. A prism just has the same base and the same top. That's it. Two congruent shapes on the top and the bottom. Think of a can, a Coke can. It's got two circles, so a circle on the top and a circle on the bottom. That's a prism. That prism is called a cylinder. Okay? So don't stress about prisms. They're pretty easy. Now, prisms also, yes, sir? The question was, can't we look at that in two different ways? Yes, we had just discussed this. We just said that. Yeah. Because if I take this here, let me just group it here real quick. And I put it on its top. Yes, I just said that. Now in this case, would this not be the base? And would this not be the top? Are the base and the top the same figures? So then this is a prism. Okay? Okay, again, we're trying to have redundant questions now. Now, what you're asking me is, oh, okay, can't this be the front and this be the back? Well, now we're talking about semantics, okay? When you look at something and you're looking at the front of it, that is the front of it. So, I mean, we're just wasting time here now at this point. No, not whatever. I'm trying to answer your question, but I don't really understand what you're asking me. How do I know? Okay, how do I know that A, B, F, E, isn't that the front? No, that's not the front? Okay. Let me ask you this, guys. Does it really matter what the front is in the long run as long as you recognize all 6 sides? If you're naming it, it doesn't matter either in a sense. Okay? As long as there's all 6 sides, all 6 faces, that's what you're going to need for later on when we're doing volume and surface area. But I will say this. You do have to learn how to recognize the base. So the base is what it's lying on. And there is no question that the base here is A, B, C, D. That is what it's lying on. Can everyone agree there? Okay, now to the right of this, right here in blue, isn't that the front? And then isn't this the back? Who could be the front too? HDC. No. HDCG is the back. Regardless, wouldn't HDCG and ABFE, wouldn't they be opposite of each other regardless of who you called the front or the back? Thank you. Okay, so we're going to move on at this point. Yes. No, that is called a pyramid. Now we're going to get to that in a second. Now, there are also edges, okay? And there are 12 edges in total. 12 edges in total. And here they are, all 12 of them. You have AD, AD, AE, AB, DH, DC, HE, HG, GF, GC, FE, FB, and BC. Those are the edges. Does that make sense? Okay. Now, you also have diagonals. And diagonals are quite particular. There's 4 in total. We know that a diagonal goes from one vertex to the other vertex. Well, since we have a space figure, you have to imagine that this box is hollow. Okay, and we're going to be drawing lines now inside of this box. Okay? The 4 diagonals here would be AB, AG, CE, and DF. Please pay close attention to what I'm doing here and the points that we are anchoring. For HB, I'm starting over here in the corner of H. And I'm going through the center of this figure and connecting to B. Does everyone see that? That is going through the center of this figure. It is not on the outside of it, it is on the inside of it. You also have AG, this bottom left corner to the top right corner, inside of the figure. You also have, these are the 2 most complicated ones, CE. Start over here at C, which is the bottom right corner. I'm going through the center to E, which is the top left corner. And the last diagonal, DF. Starting over here on the left bottom corner, D, I'm going through the center to the top right corner, F. So those are diagonals. Now, I'm going to show you in a second how these diagonals work, because it's going to be very important for setting up right triangles. In the end, remember, we're talking about a prism. We're talking about 3 dimensions. Okay? We have a length, a width, and a height. So please remember that. Okay? We have 3 dimensions here. It's a 3D figure. And the diagonals that we're creating are going inside of this figure. Okay? They're not going through anything. They're going through the center into the empty space. It's like if you have a box and you get a string and you tie it on one corner and you go through the center of the box and you attach it to the other corner opposite of it, that's a diagonal. Okay? Does that make sense, gentlemen? Okay. Now, a cube. Okay, a cube is a rectangular solid in which all edges are congruent. Now, I found this figure to be very helpful. These diagonals that I'm talking about, it does not matter whether it's a rectangular solid, or a cube. The diagonal is going to have the same effect. Okay? When I have a diagonal coming from this corner over here through the center to this corner over here, and I connect it to the diagonal of the base, I'm going to form here a right triangle. So again, D, which is the prism diagonal, goes from one of the vertices, one of the corners, through the center to the opposite corner. And when you connect that with the base diagonal, okay, you create a right angle with that common edge. Does that make sense so far? Because this is what we're going to be creating. This is how we're going to be solving a lot of things. Yes, no, maybe, kind of, sort of? Okay. Now, before we get to problems, let's talk about a rectangular square pyramid. Is this what you were talking about, Oscar? Okay, this is not a prism. Why is it not a prism, gentlemen? Thank you, because it does not have both base and top that have the same figure. Very good, very good. Thank you. Great job. A pyramid has some terminology as well, gentlemen. Okay. This point up here is the apex. It's the highest point you can get to in a pyramid. It is also called the vertex. It is the top of the pyramid. Pretty simple. But you got to know that question, okay? It's the vertex is the top of the pyramid. The base, well, the base is pretty self-explanatory. This is the base right here. The base is what it is lying on. So in this case, this is called a rectangular square pyramid because there is a rectangle or square as the base. I can have a triangular pyramid too, where the base would be a triangle. I can have a hexagonal pyramid where the base is a hexagon. I can have a pentagonal pyramid where the base is a pentagon. Okay, so the pyramid gets its name by the base. Does that make sense, guys?
Yes.
Okay. Oscar, did that answer your question?
Yeah.
Thank you, sir. Okay. So now, just like we created right triangles in the rectangular prism, we can create right triangles with our pyramids as well. Okay, let's look at this and I'll color code it. Slant height. Slant height, guys, is this line right here, S, and it is literally on the face. It is the height of the face. It is the height of the face. So the slant height is the height of the face. Okay? And H, which I'll do in red, H is the height of the figure, the height of the pyramid itself, or the altitude. So when I come down here, and I do a straight line here to the base, create an altitude, that's my altitude. That's the height of the actual figure. Look at what happens here, guys, because it's really important. With the slant height, I can create a right triangle with half of the base and the connecting edge. See that right triangle right there? I can also create a right triangle coming here with the altitude, and then from half of the base cutting across to the slant height, and now I have another possible right triangle. So I've got two possible right triangles that I can create here using the slant height, the edges, half the base, and the height. You had a question? Yes, sir.
Is slant height always going to be an altitude?
No, the slant height, is the slant height always going to be an altitude? Okay, that's, the terminology is a little bit weird there. The slant height does create a right angle. It is perpendicular to the base, but it is not an altitude because the altitude is the true vertical height. Okay, but yes, in essence, it is an altitude because it creates a 90, my brother. I just don't want you to get confused with the actual altitude of the pyramid. So if you want to say the slant height is the altitude of the face, okay, I give it to you.
Create an angle, a right angle inside the triangle, right? If you want to create a right angle on the base.
Yes, sir, you can only create the angle on the base, but I could have a base later on put in right here in the center, but we'll get there. Okay? Yes, sir. Would the faces be isosceles? Who's the question? Yes, sir, they would. Absolutely, my brother. Thank you. Great question. Does that make sense, gentlemen? Let's get to actually working some problems, and then that may make it a little bit easier, okay? Because right now it's very theoretical. Let's see how the heck it works. Okay, for problem 1 here, guys, they give you the following rectangular prism. And, you know, I tried to draw it to the best of my ability, so I'm sorry if I if it didn't come out perfect. They say that the dimensions of the rectangular solid are 3, 5, 7. It doesn't really matter where you assign these numbers, because in the end, when you're finding volume and when you're finding surface area, you're just going to multiply the numbers together. But I always try to use logic. Okay, so we got 3, 5, 7. So I'm thinking 3 would be AD, 5 would be the height, and 7 would be AB. That's what I'm just thinking off the top of my head. You know, it looks relatively reasonable. So that's the way I'm going to go. They want you to find the diagonal. Okay. They want you to find the diagonal. When they're talking about the diagonal and they give you a prism, they're talking about the actual prism diagonal. Okay, gentlemen? So the diagonal here that they gave you, they drew this. I just want to draw it for you so you can see what's happening. It's HB. So again, my anchor points are right there. All right. Now, I want to find this diagonal. Let's see what I can do here. I know that if this is 5, that means that this is 5 as well. Correct, my brothers? And then can't I create a base diagonal right here? And then I create a right triangle. Thank you very much, sir. Now, very good. You may be looking at this and say, okay, but now what, Morrow? Well, look at what we just created here. This is a 90 as well. So how do we find dB? That's the first thing we got to find. Pythagorean Theorem, thank you. dB squared equals, well, actually, no. It's 7 squared equals 3 squared plus dB squared. So 49 equals 9 plus dB squared. So 40 equals dB squared. Take the square root of both sides. 4 times 10 is 40. So dB is 2 radical 10. Okay, I'm going to stop right there for a second. Yes, sir. Questions? I'm sorry? Is BAD? Correct. Correct. Sorry about that. Thank you, guys. Yeah, because it's a rectangular. Yes, Morrow. Epic fail for Morrow. Yep, that's a rectangle. Morrow should learn how to pay attention. I apologize. Let's do it again. Thank you, guys. Good catch. Okay, so I was right in the beginning. I should have stuck to my guns. dB squared equals 3 squared plus 7 squared. So dB squared equals 58. So dB equals the square root of 58, which is going to be 2 times 29. So nothing's... I'm sorry, son? Come again? Okay. So that is what dB is. So now that we know what dB is, how do we find now HB? HB is the hypotenuse, so HB squared equals 5 squared plus square root of 58 squared. So HB squared equals 25 plus 58. So HB squared equals 83. And HB equals the square root of 83. And that is your answer. We would have gotten to a lot quicker had I not made that very silly error. That was pretty stupid of me. I'm sorry. I'm sorry, son? No, you cannot reduce that because 83 is actually a prime number. Okay, does that make sense, boys? Yes, no, maybe, kind of, sort of? Okay. Awesome. Now, let's see how it works here with a pyramid. I've got this pyramid here, and let me go ahead and label it. We've got P, O, J, K. They have a diagonal, which I'm going to do in red. I mean an altitude right here. And then it connects here. And they also give you a slant height. And you know it's a slant height. They draw this out. Okay. So then this is R. This is S. And this is M. Okay, this is given to you. This is what they gave you. I drew the inside triangle in red to kind of help illustrate, okay? Again, this is the altitude. So it's going straight up and down. It's the height of the pyramid. This is the slant height. It's the height of the face, okay? And then these 2 points are just literally half of the base. It is half of the base. Okay, so they say that a regular square pyramid shown with altitude PR and slant height PS, the perimeter of JKMO is 40. So the perimeter of JKMO equals 40. They tell you that PK equals 13. They want to find JK, PS, and PR. Okay, so let's try to break this down. If the perimeter of JKMO is 40, what is each side of this perimeter? Okay, so 10, right? So 10, 10. 10 all the way around. I don't want to put too many numbers to confuse things. Does that make sense? So JK done is 10. Okay, now I want to find PS and also PR. So how would we find the slant height of PS? Let's look at the right triangle here that we can form. Don't we know that PK is 13? And don't we know that if I take this slant height, which is an altitude, which creates a 90, and I take half of the base, I connect it with this PK, what would PS be then? 12, absolutely. This KS is half of the base, so that's 5. I know that PK is 13, so this is a 5, 12, 13 triangle, so PS would be 12. Does that make sense? And last but not least, PR. Well, now I know that PS is 12. I know that RS is 5. Now, it is tempting to say, oh, it's 13, but no, it's not 13, because the hypotenuse here is 12. So for C, we're actually going to have to calculate 12 squared equals 5 squared plus PR squared in this case. So this is going to equal 144 minus 25 equals PR squared. So 144 minus 25, we got 119 equals PR squared. Square root of both of those, PR equals the square root of 119. And that's that. Does that make sense? Yes? You guys want to do another one, or are we good? We're good? We're good. All right. God bless you. Awesome.